Listen-only mode.
Okay, good afternoon everyone, or good morning depending on where you're located. My name is Jeffrey Burke. I am the Executive Director of the National Pollution Prevention Roundtable, and today's webinar is entitled Advancements in Alternative Plastics. We have two speakers, Ramani Narayan from Michigan State University Department of Chemical Engineering and Material Science, and also Tony Kingsbury from Tony Kingsbury Consulting. All participants are in listen-only mode, so if you have a question, please use the chat or question feature that's part of GoToWebinar. After Dr. Narayan speaks, we'll open the for a couple questions. Then we'll go to Tony Kingsbury, and then we'll conclude with additional questions. Questions for Tony, and then any additional questions for both of the speakers. Since this is being presented by the National Pollution Prevention Roundtable, I want to ask Michael Simpson to speak a little bit about the roundtable and the plastics work group that is being developed. So, Michael?
Hi, welcome. My name is Michael Simpson. I'm an executive board member for the NPPR. We're excited that you're going to join us today. This is our second webinar on plastics. NPPR is the foremost leader in P2 type opportunities, pollution prevention. We just finished a state-of-the-art green chemistry manual for assistant providers. If you go to p2.org, you can see that green chemistry manual. This is the NPPR Plastic Works Group. We invite you to join us as we investigate how we can make plastics more benign and how we can reuse our plastics. If interested in joining this dynamic work group, please see the contact information on this screen. I'm Michael Simpson, and I have an outstanding student intern, Susanna Vargas, who's also assisting with us, this plastic work group. We'll be discussing topics such as what are water treatment plants experiencing, wastewater treatment plants experience as plastic toxicity. What do you do with the microbeads? How do you test the microbeads that we find in our waste streams? Our end goal is to create like a manual or working papers for assessing plastics in water treatment plants and in other media. So we want to have a great handle on plastics, how to get to more benign green plastic and how that can affect the whole ecosystem and sustainability. I'd like to thank the speakers today for participating in the webinar and sharing their expertise in alternative plastics. And I think this is going to be a great venue, and I'm looking forward to the presentations. Thank you.
I guess I'm on. All right, my name is Ramani Narayan. I'm with Michigan State University. And up front, if you have any questions you're going to ask, but if you feel free to email me at narayan@msu.edu. This presentation is, if you send me an email, I would be happy to send this presentation to you as well. So let's get started. I want to first talk about basics, the terminology of what we're going to talk about. We're talking about bioplastics, which is a subset of the plastics itself, and how and what the value proposition for this is. So the term bioplastics encompasses two separate but interlinked concepts, and the key phrase is separate and also interlinked. The first is what I call bio-based plastics, and this represents the beginning of life of the plastic. Basically, we are focusing on what is the origin of the carbon feedstock or resource that goes into manufacturing the plastic. This also refers to primarily plant biomass feedstock versus petrofossil feedstock. The second component of bioplastics is termed biodegradable compostable plastics, and this represents the end of life. So you have the beginning of life, which is bio-based, which focuses on the origin of the carbon feedstock, and then you have the end of life, and one of the end of life options is biodegradability, compostability. And the value proposition for this end of life option is zero waste solutions, for example, where you ensure that the food and other bio waste are diverted from landfills to some value-added use, because as you are all well aware, sending organic waste into a landfill where it breaks down very fast in an anaerobic environment generates methane, which is 23 times worse than CO2 as a global warming gas. Biodegradability and compostability as an end-of-life option is useful in plastic culture, where you're looking at soil biodegradability. Marine biodegradable, I put the question mark there because it seems a very nice solution. You use it, and when it goes into the marine environment, voila, it disappears, it biodegrades. But it's not as simple as that, as I hope to point. And most importantly, I do want to alert this group and to the listeners that there's a lot of misleading and false claims, additives which are claimed to be added to polyethylene to making it completely biodegradable. So this is kind of the broad overview of what I'm going to talk about. One point which needs to be stressed is that not all bio-based plastics are biodegradable, compostable. The end of life is recycling, which you are all familiar with. By the same token, not all biodegradable, compostable plastics are necessarily bio-based. So we talk about the terminology, and we're going to talk about first bio-based plastics. As I said, it refers to the beginning of life. It refers to what carbon feedstock is going to be used to make my product, plant biomass versus petrofossil feedstock. And essentially, what we're talking about is replacing the petrofossil carbon from the feedstock with plant biomass carbon. So it is substituting the carbon in the polymer molecule with bio-based carbon. So polyethylene, PET, which is your bottle, PLA is a new polymer. This is a polyester. This is bio-based polyurethanes. So basically, we're talking about carbon, and we're talking about substituting carbon of a petrofossil origin with a plant biomass origin carbon. So then the question comes, so what is the value proposition for bio-based plastics? I mean, what is the value of selecting a plant biomass carbon feedstock or resource for the manufacture? And in detail, it is presented in these papers, but essentially, I will summarize it with 2 points. And this is sort of your key take-home message here. The value proposition arises from removing carbon present as CO2 in the environment and incorporating it into a polymer molecule via plant biomass photosynthesis. And this is the most important point, in a short time scale of 1 year if you're using agricultural crops or algae or similar carbon plant biomass feedstock, to 10 years, which would be like a short rotation wood and tree plantations, in harmony with the nature's biological carbon cycle. So this is removing carbon and putting it into a polymer molecule at a rate and time scale which makes sense, which is in harmony with nature's biological carbon cycle, and offers a value attribute. Now, plastics made from petrofossil resources, which are also formed from plant biomass, but over millions of years. And so you cannot credit any CO2 removal from the environment, even over a 100-year time scale. And I want to remind the listeners that the time period used in measuring global warming potential, GWP1, is a 100-year time scale. So this is the value proposition. Now let me illustrate this value proposition with a schematic. So this is what I call understanding the value proposition for biocarbon versus petrofossil carbon. This is the biological carbon cycle. We studied this in high school. Carbon is present in the environment as CO2. Sunlight energy, photosynthesis gives you organic carbon, right? This is the biomass, ag, forestry crops, and residues in new carbon. The rate and time scale of this happening is 1 year if it is an agricultural crop, 10 years if you have forestry and rotation type materials, and we can go directly from this to making our products, which is the bioplastics or bio-based plastics that you're aware of today. Over millions of years, this biocarbon is fossilized to give you fossil resources. Oil, coal, natural gas is the old carbon. And this can also be used to make products. So we are simply submitting that by using plant biomass new carbon, every time I make 1 kilogram of product, just on a carbon basis, I am going to be removing some mass of CO2 from the environment to go in there. If I did this, I don't get any credits or should not take credits because this fossil carbon has been formed over millions of years. It cannot be related directly to CO2 removal in the environment in the present time scale. So this is what we talked about earlier. Well, what happens to end of life? So after use, these can end up back as CO2 into the environment within 1 to 10 years. This is what is happening today. And then the question comes up is that by using plant biomass carbon, A, you are removing CO2 and putting it into a polymer molecule, but B, when it goes back into the environment, because the rate and time scales of CO2 utilization is in balance with the biorenewable feedstocks as opposed to the fossil feedstock. So this is basically what I call the material carbon footprint and provides you the value proposition of the switch from a petrofossil resources to a plant biomass resource. Remember, I'm just talking about the material carbon present. I'm not talking about the process of converting this plant biomass to product, because that also has to be taken into account in terms of impacts on the environment. All right, so moving forward, here is an example of using sugarcane plant biomass resource, which was commercialized by Braskem, one of the large polyolefin manufacturers. They're going from sugarcane to ethanol to ethylene to polyethylene. So this is bio-based polyethylene. In fact, the carbon here is from a biomass carbon feedstock, right? Now, what is the value proposition for this in terms of what we have just discussed? I will let you read up on the investment and where they are later, and I guess the next speaker, Tony, will address this in more detail. So, I don't know how many of you are chemists in the audience, but if I did a simple stoichiometric balance, that means I start with carbon present in the atmosphere as CO2 and go through photosynthesis, hydrolysis to sugar, fermentation to ethanol, dehydration to ethylene, and then polymerization. This is the sequence of reactions to go from CO2 in the environment all the way to polyethylene. And I do a mass balance, a molar balance around this. I noticed that for making 28 kilograms of polyethylene, I will remove 88 kilograms of CO2 from the environment. In other words, for every kg of biopolyethylene manufactured, there is 3.14 kgs of CO2 removed from the environment. This is a clear value attribute or proposition for the switch. Obviously, there is going to be impacts on the environment going through these steps, and you need to calculate that. But that is what I call process carbon footprint, but you need to clearly recognize this is the value proposition for biopolyethylene. Now, I can extend this concept to all of you are familiar with the concept of plant bottle. All right. This is the molecule of a plant bottle, which is PET. Notice that today, only 2 of those 10 carbons present in the molecule is bio-based or bio-based carbon. The remaining 8 are still fossil petro-based. And so you will see the bottle have a statement up to 30% plant-based, mass-based bottle. Now, is there any value for replacing only 2 carbons out of the 10 carbons? The answer is yes, and I will put it in 2 ways. If you looked at 37.5 million tons of PET used for manufacturing bottle, this 2 carbon replacement will result in 17.2 million tons of CO2 removal from the environment, equivalent to 40 million barrels of oil per year savings, right? You're not solving the total environmental problem, but it is a step in the right direction. Remember, this is not biodegradable or compostable, and the end of life needs to be defined, and that is the recycling. All right. Take it further. You remember I talked to you about stoichiometrics, and I won't repeat this for lack of, or for constraints, time constraints. But if I do a net stoichiometric balance, the ingredient to make PET is this ethylene glycol, which you see identified right here, right? To make 124 kgs of this ethylene glycol, I will have removed 176 kgs of CO2 from the environment. In other words, for every kg of this bio-based ethylene glycol manufactured, 1.42 kilograms of CO2 is removed from the environment. And if you do it on the total bottle basis, 0.46 kgs of CO2 is being removed from the environment. Give you another example. You've heard of Ford introducing bio-based polyurethanes. This is the polyurethane molecule here. They have introduced it in headrests, in seat backings, and in a number of automobiles already today. The carbon being replaced is this component, the diol component. This R group is a carbon, and this carbon comes from plant biomass feedstocks. The isocyanate carbons are still petrol-based. And if I go back and do the same stoichiometric calculation, I notice that if I have 2 carbons in my diol component, I remove 1.42 kgs, and if I increase the amount of carbon in this diol, I would be removing as much as 2.77 kgs per kg of polyurethane I'm manufacturing. So again, the value proposition for bio-based plastics. Now, all of these products are not biodegradable, compostable. Here is a new polymer, recent new polymer. NatureWorks has commercialized this with a 150,000 ton polylactic acid plant. The chemistry is shown here. This is your PLA molecule. It's very similar to PET, except that it has some different groups attached to the backbone. okay? And you can see the number of products which are already in commercial use. This is bio-based because the carbons are coming from a plant biomass feedstock, and it is biodegradable, compostable, and we'll talk about that in a minute shortly. Now, this work has been done at MSU previously and is, of course, been taken up by Cargill NatureWorks to commercialize this technology. And again, if we go through that same stoichiometrics we talked about, for every kg of PLA manufactured, which is what you see here, 1.83 kilograms of CO2 is removed from the environment. Okay, now the biodegradability, compostability part comes in here. So we'll go more in details of this, but if you put this in a compost environment, then say a plasticware in conjunction with other food waste going into composting will completely be assimilated by the microorganisms present, and you can see this for a plastic film. You can see this for a molded article as well. Now, interestingly, as many of you may be aware, the USDA has a program called the BioPreferred program, where this certification is provided for bio-based products. Okay, so another information piece for you to carry is, if we are talking about bio-based plastics, we must have a method to measure this. Without that, anybody can claim anything. And I'm going to skip this in a quick way because, again, of time constraints. Happy to answer questions. But basically, this analytical methodology is based on the fact that in the atmosphere, our stable isotope carbon is in equilibrium with radioactive carbon, okay? And the half-life of radioactive carbon is 5,730 years. Therefore, any plant biomass carbon will still have this radioactive carbon signature associated with it. But remember, fossil resources, petroleum, natural gas, coal, are formed over millions of years, and therefore they will show no radioactive carbon signature. And this was then codified by us into an ASTM standard to measure bio-based carbon content, which now forms the basis for ASTM, ISO, and the European standards as well. So what I'm submitting to the group is that one can use a simple analytical methodology to identify and quantify what is the bio-based carbon content of your product, and therefore allow you to calculate using stoichiometry how much of CO2 has been removed from the environment. Okay, the next take-home point for you in this one slide which I'm trying to capture is that whenever we talk about bio-based plastics or bio-based products, the question always comes, what about land use? And is there a major problem? And I want to illustrate this, that this is the number. Don't look on the left-hand side, on the right-hand side. Let's assume that we make 119% of all polyethylene, all the plastics. Then the amount of land used to produce 125 million tons of ethanol will be somewhere around the order of 45 million hectares of land. And I would submit to you that the USA alone has 165 million hectares of arable land. The world has 1.5 billion hectares of arable land. They have another 3.1 billion of total arable land available. I want to emphasize that this is essentially decoupling, removing the coupling with fuels. So yes, if you're talking about replacing the entire fuels business or the fuels market, then issues of land use and all will certainly come up. But if you're talking about a biorefinery producing food products and industrial products, then the issues of land and all the environmental issues associated with it should not arise. And I would want the group to really take that into consideration when you hear the debate of food versus fuel or land use and things like that. The other take-home message in this, again, is to alert you to the fact that what I'm talking about today is this material carbon footprint. That is, what is the origin of the carbon going through this route versus going through that route. And you have already clearly seen this value proposition. What I am talking about is that this process of converting this feedstock to end product and then recycling and all, that is the process carbon and environmental footprint which still needs to be done, all right? And it has to be equal to or better than what exists today, not to take away from that fact. But the fundamental value proposition comes from this front end of this graph schematic which you see. All right, so I want to switch gears to talk a little bit about end of life, right? So we talked about the beginning of life and the value proposition for bio-based. Let's talk about end of life. And right off the bat, I need to let you know, if you're not already aware of this, biodegradability is the most misused and abused term in the bioplastic space, right? Degradable, partially biodegradable, eventually biodegradable, are abound in the marketplace. It should not be accepted. It has serious environmental and human health consequences, so beware and be warned. That's the message to the group, right? And you can read a lot of publications, Philosophical Transaction, Royal Society, Biology. Chelsea Roman recently published a paper in Nature which talks about issues relating to that. And therefore, both in California and at the U.S. Federal Trade Commission, the use or the unqualified use of the term biodegradable is wrong, misleading, and deceptive. So simply calling something biodegradable without telling you, without informing about what disposal environment are we talking about, what time will it biodegrade in what time scale that's going to happen. If you don't give that, then calling something biodegradable has absolutely no meaning, but it is proliferating in the market space, and you need to be aware of that. And the regulations and regulatory bodies are doing things to make sure that this doesn't happen. So the Federal Trade Commission, the state of California, have and are prosecuted companies making such false and misleading claims. The Federal Trade Commission recently sent letters warning 15 marketers of the so-called oxo-degradable plastic waste bags that their oxo-degradable or oxo-biodegradable claims may be deceptive. And the FTC is currently prosecuting another additive claim company for claims that their additives will make plastics, today's plastics, 100% biodegradable in landfill. And the key phrase they use is in 9 months to 5 years. So one has to be very careful and cautious about it. Biodegradability does give you a value proposition, but it is being totally misused and abused, and every one of us needs to be aware of that. So let me elaborate further on this issue. So where does the end of life and biodegradability fit in? So there are ASTM and international standards and specification to scientifically establish the extent of biodegradation, which is never mentioned in many of these so-called biodegradable products. So the extent, time, and the responsible disposal environment. And this word responsible is very important. And the question is, as you have heard today, there is a big issue on plastics going into the marine environment, and California, this is a bigger issue. The question is, what if I make biodegradability in marine? Is that a good, valid claim? And I would submit that marine environment is not a responsible end-of-life disposal option. In other words, you are not going to say, well, I throw it in the marine environment, it's going to go away in some time, so on and so forth. There are issues with it. So what is a responsible end-of-life for biodegradability? It is composting, it is anaerobic digestion, it is soil for specific applications like plastic culture, and it is good for zero waste solutions where you want to take food and bio waste and make sure they're all diverted from landfill through composting or through anaerobic digestion. So again, all bio-based plastics are not biodegradable, compostable. Their end of life is recycling. So biopolyethylene, bio-PET, bio-PU are not targeted for biodegradability. They are targeted for recycling, or if nothing works, a waste-to-energy recovery system. Now, the Federal Trade Commission does allow qualified biodegradability claims to have made in responsible environments. But they also say, which is, I'm very pleased with this, that science agrees with regulatory bodies here, that you must provide reliable and competent evidence. And here's the key phrase: rate and extent of biodegradation in the target disposal environment. So showing some biodegradability or simply stating it without providing actual scientific data, what is the rate, what is the extent, what is the disposal environment, is very misleading and should not be allowed, right? So this is, you have a graph, and we'll talk more about both of this in a minute here. Okay, so a quick sort of a scientific review of what does biodegradability really mean. So microorganisms utilize carbon as food to extract chemical energy for their life processes. They do not do it because they want to clean up the environment. They do it because they want to survive, and they're the most ubiquitous organisms in the planet. How do they do it? They do it by transporting the carbon inside their cells. Mind you, it has to go inside the cell, and under aerobic conditions, that is in the presence of oxygen, they oxidize the carbon to CO2, which releases energy that is then harnessed by the microorganism for its life processes. Under anaerobic conditions, CO2 and methane is produced, and again it releases energy which is harnessed by the microorganism. It's very similar to us eating food, which is then digested in our body, releases energy, and that energy is used for our life processes. So very similar process. So here is what we show it schematically or in an equation way. So I take carbon in the cell, it is oxidized to CO2. Look at this, it releases 686 kilocalories of energy per mole of this carbon substrate. And this energy then goes into a complex biological cycle which allows the microorganisms to harness the energy. Same holds true for an anaerobic process as well. So if you understand this very basic biology, which is taught in every high school, college biochemistry or biology course, then you will say, well, if you want to claim biodegradability, then show me a measure of the rate and amount of CO2 or CO2 plus methane evolved as a function of total carbon input into the process. And this should give you a direct measure of the rate and extent of biodegradation in that specific disposal environment. And if you don't have this data, then it is meaningless to claim biodegradability. So all the standards are based on this kind of testing protocol. On the right-hand side, you see a flask, you put compost, you put soil, you provide your test material into it, you put oxygen, and if the microorganisms present in this flask are capable of using the carbon substrate by oxidizing it, then you should see CO2 evolution. So by measuring how much of the carbon input is evolved as CO2 on this axis, here's where you see it, as a function of time in days, you can actually find out how much of the carbon in your test material is being utilized by microorganism as measured by the evolved CO2. So the level of biodegradation needed to claim safe and efficacious removal of carbon from the environmental compartment is around 90%. And this is the same for detergents. This is the same which EPA has prescribed for chemicals. So there's nothing new or novel except that this has been fine-tuned for plastics and biodegradable compostable plastics. And here you see all the standard numbers associated with this. So this is measuring rate and extent of biodegradability. So here's where the hype comes in, and this is what I want to caution to inform this group. A paper published in Chem Communications, a very respectable chemistry journal, shows the following, and it says the hypothesis was developed and successfully tested to greatly increase, note the word, greatly increase rates of biodegradation of polyolefins by anchoring minute quantities of glucose onto that, and so on and so forth. So here is your polyethylene or polypropylene. You hook sugar molecules into it. You measure some weight loss, that some sugar is being taken up, and then you make a claim, oh, it's biodegradable. And the press comes out and says, sugar turns plastics biodegradable, bacteria make a meal of sweetened polyethylene and polystyrene. So this is the kind of misleading, false claims that is going out. There is some biodegradation, no question about it. But is the rate and extent of biodegradation sufficient to make an environmental claim? That's where things are being sort of confused and not applied strongly. So here's another example which I wanted to show you. This is percent biodegradation on this axis, and typically, remember we said you feed your carbon to the microorganisms. If it is capable of utilizing it, it's going to take it inside the cell, it will oxidize it to CO2, you measure that. So this is percent biodegradation. And if you take a control like cellulose or regularly biodegrading, you can see that the curve goes to 80 to 90%. Now, here's what the problem is. Here is a green line which shows some biodegradation, and you'll always have some percent biodegrading in any organic plastic or anything. There may be plasticizers, there may be some loose ends, they will always show you something. But look what happens, it plateaus out. Now, if I show you this and I stop the experiment somewhere here and draw a dotted line, extrapolate this point and say, oh, look, it is biodegrading and now it will become 90% in 5 years. This is totally, even at high school levels, will not be acceptable by anyone. But we do see these kinds of things in the literature, in the marketplace, and if you let the time scale proceed, it's going to be flattened out. So one has to be careful of that. There are true biodegradable compostable plastics in the marketplace, which is now being used in California, in the world itself, like PLA, like polyesters. There are a number of products, but they meet the curve shown by this red line up there, and they have to be within a time frame defined by the disposal environment. Okay, so the take-home message for biodegradability is as follows. Right? Biodegradability is an end-of-life option, clearly, for single-use disposable packaging and consumer plastics that harness microbes to completely utilize the substrate and remove it from the environmental compartment. It enters into the microbial food chain. Very clearly a positive way of removing your carbon substrate from the environment. However, biodegradability must be defined by a disposal system, and the responsible disposal systems are composting, anaerobic digester, soil. Be very careful. It has to be like in, say, an agricultural mulch application, right? The time required for complete microbial utilization should be short. In the case of composting, it is defined as 180 days. In the case of soil, up to a maximum of 2 years. This is not yet fully agreed on, but that seems reasonable. But you must ensure complete utilization, because otherwise you're going to leave remnants of the plastics in the soil, which has got consequences. And those consequences of plastics getting into the marine environment, being assimilated by the fish and other marine mammals, and then moving up the food chain is, you have seen many, many such stories abound in there. So degradable, partially biodegradable, or will eventually biodegrade is not an option. It does have serious health and environmental consequences, and so as documented in the literature. So that is the take-home message. 2 points finally to make. One, bio-based plastic refers to the origin of the carbon in the plastic. It has a value attribute. You still have to work out the process carbon footprint. Biodegradability, compostability in a responsible disposal environment with a specific time period, and the percent biodegradation defined is useful, but there are a lot of misleading false claims which people need to be aware of. So that was a fast, quick trip down bioplastics lane, and I'm happy to turn it over to Tony or take questions. Or you can send me questions by email later as well.
Okay.
Thank you very much.
Thank you, Dr. Narayan. At this point, we don't have any questions, but if anybody does have a question, if you want it answered now, you can use the questions or what? Okay, I do have questions. So you, Dr. Narayan, you have submitted that marine disposal is not responsible. This is true, but it still happens and can't be ignored. Given the municipal solid waste and recycling programs in the U.S., this is not as much of an issue, but in countries like China, Indonesia, and the Third World, etc., where municipal solid waste and recycling programs are much less common, this is a very big problem. Therefore, wouldn't the ability to degrade
in a marine
more rapidly in the marine realm be important?
So good question, and time constraint didn't let me elaborate on it. Let me give you a good answer to that one. Clearly, one cannot target marine environment as a disposal environment, like you do composting. And the reason is very obvious. What is biodegradable in a regular lab-scale environment, in the marine environment, like in the oceans, which is temperatures at 0 and sub-zero temperatures, probably the rates is going to be very slow. It is going to last in that marine environment for years, maybe more, maybe less, all right? So if, as an industry, we say, oh, marine is a good environment, it will go away, then I think that is not the right approach, and it is be misleading, because then every stakeholder just thinks that throwing it into the ocean will take care of itself. Now, making something not stay as long in the marine environment, opposed to something which is more persistent in the marine environment, may have some value. So a claim which says that if this plastic is inadvertently lost in the marine environment, then the laboratory scale data tells us that this will stay in that environment from 2 years to 5 years, and this I'm just picking numbers, and therefore, and that's it. That's the statement one can make. Now, obviously, in the 2 to 5 years, it can still cause problems. So it's not a total solution, but it is better than something staying around for a long, long, long time without being removed from the environment. So clearly, the value attribute of a plastic to be marine, to be degraded in the marine environment to some extent, completely, after a certain period may be useful. But it certainly should not be made as a disposal environment. In fact, the efforts of the industry has to be to make sure, whether it's China or India or anywhere else, has to make sure that they don't end up in the marine environment for those consequences.
Okay, thank you. Now I'm going to turn it over to Tony Kingsbury.
Great, thank you. Thanks, Ramani. There we go. So just trying to take this up to a little bit higher level. I'll try not to use too many pictures of molecules as we explore alternatives to plastics. As Romani said, I'd be glad to share my slides with anybody. Feel free to email me, and I'll be glad to share the slides. Since Romani covered the bio-based and biodegradable, I'll cut that out. I think that, as he pointed out very clearly, that this is a common mistake that's made, that people refer to something as being bio-based. They think that it means biodegradable, and it doesn't. And it has consequences, big consequences, in terms of what we're looking at in terms of the plastics that we want to specify in given applications. So, the way I look at this is, so often the most common, I live here in California, I run into the PLA cups. The PLA cups, they look like the picture there. They're derived from corn, as Romani kind of went through the process there. They are compostable. As Romani said, I don't like the word biodegradable because it's not well defined. Compostable is well defined, and for plastics there are ASTM and ISO standards in place that if you're going to head down that path, you should make sure that the plastics meet those specifications. There's an organization, BPI, that monitors this and certifies various items to those standards, and I recommend, if you're going to specify those, that you use items that are certified by BPI. Just as a way of my own checking too, and one of those things that we need to think about is litter, right? Because oftentimes I hear from folks that if these items are inappropriately littered, whether it's on land or in sea, the hope is that if they're compostable, then they will magically disappear. So much to my wife's consternation, I actually took one of the PLA compostable cups, and it is compostable in an industrial composting facility, and you can see there's a stake through it on the left-hand picture. Staked it in the ground on the side of my house, and every month went out and took a picture of it. And you can see the picture a year after I originally staked it on the ground. So it went through summers, winters, falls, rain, snow, everything. And about the only thing that happened was the paint on the outside turned from a kind of bright green to a faded green. So the point being here, and I did the same thing with a compostable plastic bag, and after a summer in a Michigan summer, it did not degrade very quickly if it's lying on the top of the ground. If you put it into an industrial composting facility, it will compost. But don't mistake composting for it's okay to be littered. So one of the things that, the good news and bad news of kind of alternatives to traditional plastics is this bioplastic segment is one of the fastest, if not the fastest growing segment in the plastics arena. The recent research report that I saw from BCC Research stated, and kind of went through in more detail than I put here, but it's very high compounded annual growth rate of over 25% from a current 347 million pounds to what they project in 5 years or 4 years to be over 1 billion pounds. I guess that's the good news. The bad news is that if you understand the scale of plastics, one or two world-scale polyethylene plants being built in the world today, and many of them are being built. They're being built in the Gulf Coast of the U.S. They're being built in China and Indonesia, in the Persian Gulf. 1 to 2 of those facilities is one global world-scale facility these days is 750 million pounds. So 2 of them would be 1.5 billion pounds. So it just gives you kind of a scale that says, this is growing, but we're not there yet in terms of the kind of scale that we're looking at. Just this morning, it came across my desk that an Italian producer called BioOn is building a plant in Italy to make a PHA that Romani mentioned, and I'll mention again. in a facility that's associated with the residue from a potato processing facility. This plant will make, when it's fully up to scale, will make 8 million pounds a year. Great for them, but are we making a huge dent? We have to realize that there's big scale here. So the two largest bio-based plastics produced today are biopolyethylene. As Ramani described, it's based on sugarcane right now, made in Brazil. Braskem has a facility down there where they take the sugar cane, ferment the sugar to ethanol, ethanol to ethylene, ethylene to polyethylene. According to the carbon footprint life cycle analysis I've seen, it's about an 85% reduction, when you kind of take into all the process energy, which is great if your goal is carbon footprint reduction. This polyethylene is molecularly the same as traditional polyethylene, which makes it fully recyclable, but it's not compostable. And so, as Ramani said, you have to make sure you understand that if you, so if your goal is carbon footprint reduction, great choice. If your goal is water reduction, it's not a good choice. There's a lot of water and land that's used in the production of these. And the same holds true for the second largest bio-based plastic today, which is PLA. The main producer of that globally, although there are a number of producers, is NatureWorks. They have a large facility in Nebraska, Blair, Nebraska. And they take corn sugars and feed microorganisms that produce the lactides or lactic acid that's then separated and converted into PLA. And there's a wide array of uses from fibers to disposable packaging, et cetera, that are made from PLA. The good news is that NatureWorks has the facility in Nebraska. They're looking at building a second facility, I believe somewhere in Southeast Asia, which is a great sign that the market's growing and that there's demand for the polymer and that applications are growing. So look forward to seeing that second facility in Southeast Asia. There's also biodegradable or compostable polyesters. This is a different form of polyester than would be in your clothing. It's a different form of polyester than PET, the soda bottle material would be made from. It has a slightly different chemistry. That slight difference makes it compostable or biodegradable. It's made by BASF. This is not bio-based though, so it's biodegradable, compostable, but it is not bio-based. They do make a version of this where they combine it with a bio-based polymer, but it's used in an additive process at that point. But again, this is a material that's commonly used or blended with other polymers that are compostable for things like bags that you would use in a composting for home composting, as an example. Where you don't want the mess that comes if you tried to put the composting in a paper bag, for example, and it would fall apart. So an example of a compostable polymer, but it is not bio-based. I show this slide here to let the bio bottle wars begin. As Ramani showed, Coke has introduced the plant bottle. After they introduce the plant bottle and have some other partners like Heinz that are beginning to use that same bio-based polymer for the PET applications, Pepsi announced that they've got a full-scale program in place to do the same thing, to make bio-based polyethylene. They're somewhat behind in that at this point, but I always think that competition is a good thing, and so we're progressing along there. The Coke bottle is as Ramani said, is molecularly the same, PET. It's 100% recyclable, but it is not biodegradable or compostable, and it has about 30% bio-based content, depending on how you measure it. Other examples that have emerged are, I just met a company in Idaho that's making a starch resin that can be blended with polyethylene. The good news about this is it's low cost. So if you blend it in with the polyethylene, you're not increasing your costs, which is a common complaint with many of the bio-based polymers in circulation today. So it doesn't increase costs. It can improve properties and can reduce. You can actually reduce weight. Another option. But again, you wouldn't be able to make claims of compostability or biodegradability because the base resin would be polyethylene, which wouldn't compost. There's examples of nylons that are being made bio-based. DSM is a polymer producer based out of Europe. They're taking castor bean and have a 70% bio-based content nylon that they're using. This would be used for durable applications like a binding for snowboarding or automotive parts, etc. This would not be targeted at compostable applications. There's emerging things like Harvard's Weiss Institute is working on a degradable bioplastic made from the chyosan, from the shells of shrimp. Again, we need to ask ourselves that you might come up with a cool polymer there, but how many shrimp shells are there, and how much could we actually make? And I don't know the answer to that. So interesting concepts, but ones that we have to think about scale and how much could we actually produce there. Another fun one, Heinz and Ford are getting together to look at can they use dried tomato skins from the ketchup making process. Heinz has all the extra skins, and can they turn that into parts for vehicle parts? My question is on a hot day in South Texas, does your car start smelling like tomatoes? I don't know, something. And again, I talked a little bit earlier about the PHAs. They're a class of polymers. You've got a number of companies that are emerging in this. The Italian company that I spoke of earlier, you've got Mango Materials and New Light, both emerging companies that make PHAs. This class of polymers, it uses either methane or is capturing that carbon out of the air, as Romani talked about, using new carbon as the source for this. These are fully compostable, but we need to get the scale up in order to get the cost down and make it competitive in the marketplace. I did a calculation a few years ago on this. This is the one polymer that is pretty marine degradable. And I agree with Romani in his explanation that we don't want to target stuff for disposal in a marine debris environment. But if we do, if it does end up there, this would degrade. The challenge that we have here is I did a calculation a few years ago where I looked at if we replaced 10% of the packaging, plastic that goes into packaging in the U.S. by PHAs, they would need to build a world-scale facility every week for 12 years to capture 10% of the marketplace. There's currently a number of these small facilities. There's no plans to build, a world-scale facility, as I would call it. That would be at least maybe 50 million pounds a year. And that's the challenge that we have in terms of getting to scale on these things and getting acceptance in the marketplace. Here's just a quick chart to kind of show there's the compostable bio-based, there's compostable fossil-based, there's durable that are bio-based, and then there's durable that are the kind of traditional polymers. I just listed a few there: polyethylene, polypropylene, and polystyrene. And then you have this kind of bio-based and fossil-based as a percentage depending on what formulation you do. So just something to kind of think about. The other thing, and I know we've only got a couple minutes here, but properties matter. Price and performance. If we look at why these bio and alternative plastics haven't emerged in a bigger way, they suffer typically from one or both of these problems, that either the price is too high as compared to traditional, or the performance isn't there. And oftentimes it's both of these, because we need cups and bottles to hold liquids, and we need it to hold for a long time, right? We need to be able to withstand heat. PLA, if you pour a hot liquid into PLA, it structurally isn't strong. So, it's okay for cold drinks, but it's not okay for hot drinks. If you're going to put soda into a bottle, you need to have barrier properties to CO2, or else your soda will go flat. Is it flexible? Is it rigid? All of these things. I show a helmet here. If you're going to make a helmet, it needs to be very strong and withstand those kind of helmet-to-helmet interactions that happen in the football field. And so we can't compromise on properties oftentimes. So it's very important. Scale matters, and Ramani talked about that. I mean, it does. If we're going to go to bio-based, then you need to have crops, you need to have sugars, you need to have something to feed the microorganisms that then create the monomers that are then used to make the polymers. And we need to think about, one of the first questions when I learned that they were going to make polyethylene from sugarcane in Brazil was, are they chopping down rainforests, to grow the sugarcane? And the answer is no, not now. But if we take these things to scale, is there temptations to start doing that? And we need to make sure that we understand when that is happening, and that there are limits to how far we can go with a lot of these things. And so we need to think about those scale things. And recycling matters. Ramani talked about that, and I would just emphasize, unfortunately, the problem is the public doesn't kind of look at the bottom and go through this. And one of these cups is PLA, one of these cups is PET. The public looks at them and they think, oh, yeah, they look the same. And so they throw them both in the recycling bin. The PLA one ends up causing contamination unless there's a system to sort it out. And until there's a lot of PLA available in the marketplace, it's tough to justify all that infrastructure that needs to be put in place to separate it out. That is just starting to happen now, and PLA has been manufactured for 15 to 20 years now. So just to understand the scale issues is important. So with that, you can read through the kind of final things that we need to be thinking about. These things don't magically disappear if they're littered. We need to think about greenhouse gas emissions. We need to think about the life cycle, and we need to understand the difference between bio-based and compostable or biodegradable. So with that, thanks everybody.
Okay, thank you, Tony. Any questions for Tony? Please go ahead and submit them now. If anybody has a question. If not, again, both speakers indicated that if you have a question, you can contact them directly. Just a reminder that this session is being recorded, and the recording will be posted up on the NPPR website. So, www.p2.org. Not seeing any additional questions. Oh, wait. No, I'm sorry. There's another question. Okay. Regarding PHA, PHB, what about metabolics? Interestingly, they recently made an agreement with Honeywell to make biodegradable microbeads.
Yeah, I saw that. They are another, metabolics is another one of the PHA, PHB manufacturers. Unfortunately, I saw that. I struggle with that application of putting microbeads in an application. So they're put in makeups or scrubs that you would then kind of use in your face, and they're the abrasion component of those. They would degrade in that marine environment, but they're designed to go down the drain and end up in that marine environment. So the question is, how fast do they degrade in that environment, and clearly they would be better than if you used another non-compostable or degradable polymer in that, which has been used by the industry and has caused the current problems. The other challenge I would think is there's a number of states that have already passed laws that are going to ban the use of plastics in those applications. I don't think that there's language in those laws that allow for degradable plastics to be used, so it may be a moot point. And their facility, again, is a pretty small producer of PHAs and PHBs compared to what we see world scale in traditional plastics. They, in fact, shut down their big plant in, I can't remember, it was in Iowa somewhere, because the economics just didn't play out.
Okay. Thank you very much, both Dr. Narayan and Tony Kingsbury, for your outstanding presentations. As I mentioned, these will be available in the next few days on the NPPR website, www.p2.org, the entire recording. The next NPPR webinar will be on April 8th at 2 p.m. Eastern Time, and the topic will be success stories in green chemistry, a couple of small companies that have successfully implemented green chemistry solutions to problems that they faced. So again, thank you everyone for attending, and hope to see you next time.